Hi and welcome to our talk. I'm Johannes.
I'm Ralf.
Yeah, and we want to show you how we brought Cloud Native Buildpacks to CF. So we are not usually doing work in the CF core area, so we were pretty new to all of the processes, the repositories, and the community itself. So what we usually do is provide tools for people who want to migrate their workloads from CF to Kubernetes. And one of those pillars are Cloud Native Buildpacks. Another pillar is a help chart and a CLI which combines those offerings together. So we have some SAP specific Cloud Native Buildpacks, but also are working in the community mainly with the Buildpacks and the Pakido organization. Working on bugs and new features and so on. Providing support inside SAP for them as well. So why bring Cloud Native Buildpacks to CF at all? It's the next generation of Buildpacks. It comes with a different architecture. So if you take the classical V2 Java Buildpack, for example, it's one big offering, I would say, one monolith, and Cloud Native Buildpacks split it apart. So there are multiple buildpacks providing JVMs, there are buildpacks which provide capabilities for building Java apps, for example, using Maven and others. There are also some buildpacks which are not available as V2 at the moment. One prominent example is the Java Native Buildpack, which uses GraalVM, for example, to build and run your workloads, your Java workloads. And last but not least, also alignment with Corifi. Corifi uses Cloud Native Buildpacks already. It's using KPack to build images out of your source code. And it's, I think, a good thing to align with them as well. A small overview. If you haven't heard about Cloud Native Buildpacks yet, it's a CNCF incubating project. There is a security audit from 21, I think, where they succeeded with flying colors. So check it out, it's in the slides, it's pretty good. So it's actually split in two projects. There's the Buildpacks project, which hosts basically the specification and some tooling around that. And then there's Pakido with implementations for Buildpacks, providing various JVMs, for example, providing Buildpacks for Node.js and many, many others. What they usually do is take your source code and transform it into a container image. And there's, I think, the first, maybe gap to Cloud Foundry, because in Cloud Foundry you usually run applications as droplets. And we worked around that, and you will see how we did that in a couple of minutes. Cloud Native Buildpacks come with same defaults, security defaults, no workload is running as root. There's a separation between the build environment and the run environment, so you can have separated stacks or separated images which form the basis for building and running, and it overall improves the security surface quite a bit. Taking a look at the basics of Cloud Native Buildpacks, so in the center there's always a platform, and for our implementation on CF we brought a custom Cloud Native Buildpacks platform to CF. There are tools or platforms like Pack, for example, on your local machine. It schedules a container, executes the builds, the Buildpacks inside the container, and produces in the end finally an image. There are many inputs you can provide to that. The most prominent ones are your source code, the Buildpacks you want to run, and in the end maybe even a run image for the final image, which the final image is based on. Alright, taking a bit of a closer look here. So the platform actually only controls the build process, and hence the heavy lifting to a thing called a lifecycle. Between the platform and the lifecycle there's an API, there's a specification. You can also check that out on the Buildpacks page. So every piece of software which behaves like a platform can then be used within the lifecycle. You provide code, you provide your Buildpacks as inputs, and in the end the lifecycle contains 5 phases. The most important ones are the detection, where each build pack is asked whether it can contribute something to the final image. So for example, if you present the lifecycle a Node.js application, the Java build pack would probably say, nah, I can't do anything here, and wouldn't detect. Another lifecycle phase is building, where then each detected build pack does something, run some actions, provide layers to the final image. And last but not least, there's an export phase, where then the final Docker image is written somewhere. In case of pack, that's the local Docker daemon, but it can also be written directly to a container registry. Yeah, looking a bit deeper, build packs can provide layers if they detect. There is also an API between lifecycle and build packs, so everything which acts according to those specifications is considered a build pack. Build packs typically ship 2 binaries in contrast to, I think it's 3 for Cloud Foundry. One is the detection logic, where it tells if it can contribute something or not, and the other one is the build binary, which then runs certain actions. Download a JVM, trigger a compilation of your Java workload, and others. So in the end, the image which is produced is based on some image, a run image or a run image layer if you want. That can come as an input as well from the user. In our case, in our implementation, we rely on CF Linux FS4, so there are no changes there. Then you have your application code on top, and whatever layers build packs contribute. In case of a Java app, that could be a JVM, that could be, I don't know, for Dynatrace, some APM agent or anything else. All right.
Okay. So both build packs, so the Cloud Foundry build packs and Cloud Native Buildpacks are very similar, but one major difference is the modality. So what's called a build pack in Cloud Native Buildpack, they have this concept called meta build pack, which is actually, in this case, the Node.js build pack is actually a collection of 13 build packs. And instead of having one monolith which does everything, each and every build pack of the 13 are asked, do you detect, and if so, you can add your build step. There are some that are optional, some are mandatory, so to say, and there are even smaller build packs like handling the environment or handling the proc files, which can then be reused in other language families or are reused in other language families, and that makes it quite easy to add your own functionality to the build process by just adding one of your own little build packs for the little aspect you want to add, and rely on the whole stuff around it. So let's have a look at the implementation, how we implemented the Cloud Native Buildpacks in parallel to the existing build packs. So we added to the manifest, I can hopefully this here. We added to the manifest one property called lifecycle, which defaults to the existing build pack, so default build packs, but you can set it to Cloud Native build packs if you want to test out the other build packs. And then the cloud controller knows what you want to do, and the staging action and the desired long-running process that are written to BBS look a bit different, like for the existing build packs. Mainly a different lifecycle is used, and the action is either builder or launcher. And then later on, Diego on the right side, so Diego can then pick it up on BBS and know, okay, another lifecycle should be called, and it's called either with the builder. In this case, the lifecycle would create a droplet, or a launcher would be called, which then would take the droplet and the stack and then create the running application over of it. Now let's have a closer look at what's going on in the life cycle we were adding. So at the CNCL, there's a repo CNB app lifecycle. It's actually, and it turned out that the CF specific changes we had to do were actually quite small. So regarding comparing to the other platforms Johannes mentioned earlier. One difference is the downloading of the needed build packs in the beginning, because the cache handling from Diego is a bit different, and the build packs might already be cached and things like that. But then the real work, so to say, so the detect restoring from the cache is found, and actually building the image can more or less just be reused from the, I just called it here, the reference implementation for Buildpack, which is basically used by all platforms out there. So this was, we hadn't to change much there at all. And then the other thing that changed, normally the export phase would be called, and that would produce an image. But Johannes will touch on this later, we decided we want to go for droplet to keep it more similar to the existing build packs, and therefore we had to exchange the export phase to export a droplet instead. And for the launch phase, binary is even easier. We could just reuse the launch command from the reference implementation. Just have a simple application for Cloud Foundry, and normally it's using, of course, the Cloud Foundry provides build packs. But if we look at the difference in the manifest, it's only just adding this property I mentioned earlier to Cloud Native Buildpack, and then providing the actual build pack. Because one thing that we will touch on later is currently there's no system build pack yet for Cloud Native Buildpack, so there's no auto detection, so you would have to provide the build packs. But then with this more, and one more thing I wanted to show. So there's a feature flag. So this has to be enabled in order to actually use the Cloud Native Buildpack. So in our dev landscape, this already enabled, so I can just push it, and then hopefully most of you are familiar with the output, and you will recognize, let's say, most of the output. So the beginning and then later the end are the same, and in between the log output from the actual build pack is obviously different, because the Cloud Native Buildpack is called instead. So that should then start any second now. And here is what we see. It's checking which build packs of the meta build pack will participate. In this case, one build pack is actually downloaded Dode engine, another thing, another build pack found a package JSON, so npm install will be called, and one build pack found a node or process to actually start, and then we can what not. And starting instances. So the output at the end is the same again as before. Okay, it was my bad. And then From this point on, you will recognize no difference anymore with what Buildpack application was actually built. To check this, I prepared a small custom user-provided service, which I can just bind service the app, which I can just and then I of course have to restage the app. And in the meantime I can fully just open the app. So there's no service bound yet, and it's the same simple application as it would look like if we would have built it with the default build packs. Okay, now it's already exporting the droplet, so it should be starting the app every second now. And then we will see that the binding, we can maybe just have a look at, just have a look at the environment. And then just like we would expect with normal build packs, we will see the user provided service here. It's called demo. And also in the, if I just refresh here, the service is found. So basically after the actual build, there's no different, should not be any difference anymore for the actual app. And then I go back to the go back to the peak.
All right, for the implementation we had a set of guidelines which we followed when implementing. So first and foremost, we wanted to introduce no drastic changes to DCF architecture to really focus on the building side, and the running side can just stay the same, like Ralf mentioned. Also, we wanted to keep features like the implicit rebase, like SSH, but on the other hand side, also keep the design pretty open to not block any further improvements. One result for that is that we decided against having a registry for images produced by Cloud Native Buildpacks, but rather stick with the droplet approach. So yeah, there's nothing we would need to change for the architecture here. The droplets will land in the blob store like any application which is built with the classical Buildpacks. We also decided against the Paketo stacks and went with CF Linux FS4 because it was just easier. For Paketo there are typically 3 flavors you can use for stacks if you want. There's a base one, there's a full one which is comparable to CF Linux FS4, but also a tiny variant, for example, and even more stripped down stacks there. But not introducing more stacks than there are here already was one of our goals. Also the discussion around how to actually bring that to the manifest or give that into the user hands. where we decided for having an explicit lifecycle type in the manifest. Also had ideas like just CMB enabled through just a Boolean flag, for example. If you're interested, you can find the discussion in the RFC. Yeah. Also, when it comes to executing the Cloud Native Buildpacks lifecycle, so it typically comes with a set of binaries where each phase is in a different binary. You can just call that. It's also provided as a library. It's a Go project, which we took and enhanced it with capabilities to export droplets instead of exporting container images. You can also have your own implementation, which is quite an effort, I guess, but the specification is out there. Can read it, can implement it, and yeah.
And then just an overview of the current state. So we have the heading is a bit misleading because second RFC is not implemented but accepted, but the first one is fully implemented. So we introduce a feature flag, and we also introduce in the cloud controller so that the new manifest property can be interpreted. And also our original plan was not have any change to Tego, just to reassure that we only touch, let's say, the building side but not the running side. And in the end, we had to touch the Tego release because the lifecycles lie on the file server, so they come with the Tego release, and the new lifecycle must be added there. But other than that, we haven't touched anything in Tego, or had to. And then it obviously was added to CFC problem, and also we added some acceptance tests for it. And it's already added to the CLI, but only in main, which is then the V9. As far as I know, there's not a release for V9 yet. So you cannot use it on the command line, for example, overriding the lifecycle type. But if you add everything you want in the manifest, it will already work. And then the other build pack I just mentioned, the Cloud Native System Buildpacks, which is accepted but not implemented yet, because we decided so we first want to implement everything fully and get some feedback from some usage before we tackle the next step, so to say, and add it as a system buildpack, which then would enable auto detection, for example. So some outlook. So like mentioned, the implementation of the system buildpacks might be one of the next steps. And what's still open is the changes to the CF docs, which turns out to be a bit more complicated because both buildpacks should somehow be in parallel, and the users should get some guidance when to use what and what are the benefits of each other and things like that. And we are thinking if we can or should downport the CLI changes to V8, which is the currently most used one probably. And with that, I guess we're so.